Conceptual design of a micron-scale atomic clock.
Abstract, a theoretical concept that will compress the whole atomic clock down to micron size. An atom of either nitrogen or phosphorus is added to a fullerene cage. Next, an insulating shell is applied to an endoferrule fullerene, and several of them are tinily deposited on a silicon chip. A GMR sensor is constructed adjacent to this layer, in close proximity to the endoferrule fullerenes. These GMR sensors detect oscillating magnetic fields from nuclear spins that vary at the frequency of the hyperfine transition, which are on the order of microgauss. This new type of atomic clock has strong vibration and shock tolerance, extremely low power, stability on the order of 10 to the power of 9, and is compatible with chip embedding and MEMS production. In response of the ongoing enhancement in sensitivity of GMR sensors, this type of atomic clock will become more reliable. Objective: the aims of this research will be focusing on several aspects associated with the development and application of this kind of clock, such as to establish a theoretical foundation for the development of micron-scale atomic clocks, and to determine the key design parameters for a micron-scale atomic clock, considering the needs for accuracy, stability, power consumptions, and size restriction. For introduction, atomic clocks have existed since 1949. The hyperfine interaction between outer electrons and nuclear spin serves as the primary timekeeping mechanism. Embodiments commonly use atomic hydrogen, alkali metals, and ions with a single outer orbital electron. However, hyperfine splitting is present in more broad atomic and molecular species and can be exploited for timing. The hyperfine interaction is resistant to vibration and temperature because it solely affects the density and spin of electrons in the nucleus. Atomic clocks are now tiny, measuring only a few cubic millimeters. DARPA and the electronic sectors are focused on decreasing the size, complexity, and the power needs of atomic clocks. For theory, an atomic clock applies a feature known as atomic resonance. Atoms can exist in multiple energy states. When an atom absorbs a photon, at the precise appropriate frequency, it will be accelerated from a lower energy state to a higher one. In an atomic clock, a beam of cesium atoms is exposed to microwave radiation. The microwave radiation's frequency can be precisely adjusted to coincide with the natural frequency at which cesium atoms shift between energy levels. When the microwave radiation's frequency matches that of the cesium atoms, a large number of atoms are excited. This can be identified by measuring the absorption of microwave radiation. Outcome: the micron-scale technique utilizes a drive voltage near the hyperfine resonance to generate a tiny 1% of the drive field signal, which is detected and amplified by the GMR sensors to provide a suitable voltage. Based on the basic physics, a fullerene signal at resonance 413 microhertz with a line wide of 6.1 Hz is expected to be in the order of 1000 Tesla. GMR sensors at normal temperature have a sensitivity of 350 pT-Hz. A 1 Hz filtered loop should identify an atomic clock resonance with a signal-to-noise ratio greater than 1. For conclusion, the proposed technique results in a micron-scale atomic clock with 10 to the power of 9 accuracy and a power dissipation of a nanowatt resonance circuits for energy storage. The most advanced nanotechnology clock comprise a single fullerene with significant insulation. This advancement paves the path for improved portable and embedded systems in telecommunication, navigation, and timing critical technologies, providing better performance while using less power.